Comet Shoemaker-Levy 9. From Wikipedia, the free encyclopedia, http://en.wikipedia.org. Comet Shoemaker-Levy 9, or SL9, formerly designated D/1993 F2, was a comet which collided with Jupiter in 1994, providing the first direct observation of the collision of two solar system objects. This generated a large amount of coverage in the popular media, and SL9 was closely observed by astronomers worldwide. The comet provided many revelations about Jupiter and its atmosphere, and highlighted Jupiter's role in reducing space debris in the inner solar system. Astronomers Carolyn and Eugene M. Shoemaker and David Levy discovered the comet, which was the 11th one they had found. It is called Shoemaker-Levy 9 because only periodic comets are numbered in this way. The Shoemaker's-Levy team has discovered 4 non-periodic comets in addition to its 9 periodic ones. Shoemaker-Levy 9 was located on the night of March 24, 1993, in a photograph taken with the 0.4-metre Schmid telescope at the Mount Palomar Observatory in California. Unlike all other comets discovered before then, it was orbiting Jupiter rather than the Sun. SL9 was in pieces, ranging in size up to 2 kilometres in diameter, and is believed to have been pulled apart by Jupiter's tidal forces during a close encounter in July 1992. These fragments collided with Jupiter's southern hemisphere over a period of time between July 16 and July 22, 1994, at a speed of approximately 60 kilometres per second, or 37 miles per second. The prominent scars from the impacts could be seen on Jupiter for many months after the impact, and observers described them as more easily visible even than the Great Red Spot. Section 1. Discovery. Comet Shoemaker-Levy 9, or SL9, was discovered on the night of March 24, 1993, by the Shoemakers and Levy, who were conducting a program of observations designed to uncover near-Earth objects. The comet was thus a serendipitous discovery, but one that quickly overshadowed the results from their main observing program. The discovery was announced in IAU Circular 5725 on March 27, 1993. Subsequently, several other observers found the comet in images obtained before March 24th, including Kin Edite from a photograph exposed on March 15th, Satoru Otomo on March 17th, and a team led by Eleanor Halen from images on March 19th. The discovery image gave the first hint that SL9 was an unusual comet, as it appeared to show multiple nuclei in an elongated region about 50 arcseconds long and 10 arcseconds wide. Brian Marsden of the Central Bureau for Astronomical Telegrams noted that the comet lay only about 4 degrees from Jupiter as seen from Earth, and that while this could of course be a projection effect, its apparent motion suggested that it was physically close to the giant planet. Because of this, he suggested that the Shoemakers and David Levy had discovered the fragments of a comet that had been disrupted by Jupiter's gravity. Section 2. A Jupiter-orbiting comet. Orbital studies of the new comet soon revealed that, unlike all other comets discovered before then, it was orbiting Jupiter rather than the Sun. Its orbit around Jupiter was very loosely bound, with a period of about 2 years, and an apogee, or furthest distance from Jupiter, of 0.33 astronomical units, or AU, 49.4 million kilometres. Its orbit around the planet was highly eccentric, with E equal to 0.9986. Tracing back the comet's orbital motion revealed that it had been orbiting Jupiter for some time. It seems most likely that it was captured from a solar orbit in the early 1970s, although the capture may have occurred as early as the mid-1960s. No pre-covery images dating back to earlier than March 1993 have been found so far. Before the comet was captured by Jupiter, it was probably a short-period comet with an aphelion just inside Jupiter's orbit, and a perihelion interior to the asteroid belt. The volume of space within which an object can be said to orbit Jupiter is defined by Jupiter's hill sphere, also called the Roche sphere. When the comet passed Jupiter in the late 1960s or early 1970s, it happened to be near its aphelion, and found itself slightly within Jupiter's hill sphere. Jupiter's gravity nudged the comet towards it. Because the comet's motion with respect to Jupiter was very small, it fell almost straight into Jupiter, which is why it ended up on a Jupiter-centric orbit of very high eccentricity, that is to say, the ellipse was nearly flattened out. The comet had apparently passed extremely close to Jupiter on July 7, 1992, just over 40,000 kilometres above the planet's cloud tops, a smaller distance than Jupiter's radius of 70,000 kilometres, and well within the orbit of Jupiter's innermost moon Metis and the planet's Roche limit, inside which tidal forces are strong enough to disrupt a body held together only by gravity. Although the comet had approached Jupiter closely before, the July 7th encounter seemed to be by far the closest, and the fragmentation of the comet is thought to have occurred at this time. Each fragment of the comet was denoted by a letter of the alphabet, from fragment A through to fragment W, a practice already established from previously observed broken-up comets. More exciting for planetary astronomers was that the best orbital solutions suggested that the comet would pass within 45,000 kilometres of the centre of Jupiter, a distance smaller than the planet's radius, meaning that there was an extremely high probability that SL9 would collide with Jupiter in July 1994. Studies suggested that the train of nuclei would plough into Jupiter's atmosphere over a period of about 5 days. Section 3. Predictions for the collision. The discovery that the comet was likely to collide with Jupiter caused great excitement within the astronomical community and beyond, as astronomers had never before seen two significant solar system bodies collide. Intense studies of the comet were undertaken, and as its orbit became more accurately established, the possibility of a collision became a certainty. The collision would provide a unique opportunity for scientists to look inside Jupiter's atmosphere, as the collisions were expected to cause eruptions of material from the layers normally hidden beneath the clouds. Astronomers estimated that the visible fragments of SL9 ranged in size from a few hundred metres to at most a couple of kilometres across, suggesting that the original comet may have had a nucleus up to 5 kilometres across, somewhat larger than Comet Hyakutake, which became very bright when it passed close to the Earth in 1996. One of the great debates in advance of the impact was whether the effects of the impact of such small bodies would be noticeable from Earth, apart from a flash as they disintegrated like giant meteors. Other suggested effects of the impacts were seismic waves travelling across the planet, an increase in stratospheric haze on the planet due to dust from the impacts, and an increase in the mass of the Jovian ring system. However, given that observing such a collision was completely unprecedented, astronomers were cautious with their predictions of what the event might reveal. Section 4. Impacts. Anticipation was high as the predicted date for the collisions approached, and astronomers trained their telescopes on Jupiter. Several space observatories did the same, including the Hubble Space Telescope, the Rosat X-ray observing satellite, and significantly the Galileo spacecraft, then on its way to a rendezvous with Jupiter scheduled for 1996. While the impacts would take place on the side of Jupiter hidden from Earth, Galileo, then at a distance of 1.6 astronomical units from the planet, would be able to see the impacts as they occurred. Jupiter's rapid rotation would bring the impact sites into view for terrestrial observers a few minutes after the collisions. Two other satellites made observations at the time of the impact. The Ulysses spacecraft, primarily designed for solar observations, was pointed towards Jupiter from its location 2.6 astronomical units away, and the distant Voyager 2 probe, some 44 astronomical units from Jupiter, and on its way out of the solar system following its encounter with Neptune in 1989, was programmed to look for radio emission in the 1 to 390 kHz range. The first impact occurred at 2015 UTC on July 16, 1994, when fragment A of the nucleus slammed into Jupiter's southern hemisphere at a speed of about 60 kilometres per second. Instruments on Galileo detected a fireball which reached a peak temperature of about 24,000 kelvins, compared to the typical Jovian cloud-top temperature of about 130 kelvins, before expanding and cooling rapidly to about 1,500 kelvins after 40 seconds. The plume from the fireball quickly reached a height of over 3,000 kilometres. A few minutes after the impact fireball was detected, Galileo measured renewed heating, probably due to ejected material falling back onto the planet. Earth-based observers detected the fireball rising over the limb of the planet shortly after the initial impact. Astronomers had expected to see the fireballs from the impacts, but did not have any idea in advance how visible the atmospheric effects of the impacts would be from Earth. Observers soon saw a huge dark spot after the first impact. The spot was visible even in very small telescopes, and was about 6,000 kilometres, or 1 Earth radius, across. This and subsequent dark spots were thought to have been caused by debris from the impacts, and were markedly asymmetric, forming crescent shapes in front of the direction of impact. Over the next 6 days, 21 discrete impacts were observed, with the largest coming on July 18th at 0734 UTC, when fragment G struck Jupiter. This impact created a giant dark spot over 12,000 kilometres across, and was estimated to have released an energy equivalent to 6 million megatons of TNT, or 750 times the world's nuclear arsenal. 2 impacts 12 hours apart on July 19th created impact marks of similar size to that caused by fragment G, and impacts continued until July 22nd, when fragment W struck the planet. Section 5. Observations and Discoveries. Chemical Studies. Observers hoped that the impacts would give them a first glimpse of Jupiter beneath the cloud tops, as lower material was exposed by the comet fragments punching through the upper atmosphere. Spectroscopic studies revealed absorption lines in the Jovian spectrum due to diatomic sulfur and carbon disulfide, the first detection of either in Jupiter, and only the second detection of diatomic sulfur in any astronomical object. Other molecules detected included ammonia and hydrogen sulfide. The amount of sulfur implied by the quantities of these compounds was much greater than the amount that would be expected in a small cometary nucleus, showing that material from within Jupiter was being revealed. Oxygen-bearing molecules, such as sulfur dioxide, were not detected, to the surprise of astronomers. As well as these molecules, emission from heavier atoms such as iron, magnesium and silicon was detected, with the abundances of these atoms being consistent with what would be found in a cometary nucleus. While substantial water was detected spectroscopically, it was not as much as predicted beforehand, meaning that either the water layer thought to exist below the clouds was thinner than predicted, or that the cometary fragments did not penetrate deeply enough. Seismic waves. As predicted beforehand, the collisions generated enormous seismic waves which swept across the planet at speeds of 450 kilometres per second, and were observed for over 2 hours after the largest impacts. These waves seemed to be gravity waves, but their location was subject to debate. The waves were thought to be travelling within a stable layer acting as a waveguide, and some scientists believed the stable layer must lie within the hypothesized tropospheric water cloud. However, other evidence seemed to indicate that the cometary fragments had not reached the water layer, and the waves were instead propagating within the stratosphere. Other observations. Radio observations revealed a sharp increase in continuum emission at a wavelength of 21 centimetres after the largest impacts, which peaked at 120% of the normal emission from the planet. This was thought to be due to synchrotron radiation, caused by the injection of relativistic electrons into the Jovian magnetosphere by the impacts. About an hour after fragment K entered Jupiter, observers recorded auroral emission near the impact region, as well as at the antipode of the impact site with respect to Jupiter's strong magnetic field. The cause of these emissions was difficult to establish, due to a lack of knowledge of Jupiter's internal magnetic field and of the geometry of the impact sites. One possible explanation was that upwardly accelerating shock waves from the impact accelerated charged particles enough to cause auroral emission, a phenomenon more typically associated with fast-moving solar wind particles striking a planetary atmosphere near a magnetic pole. Some astronomers had suggested that the impacts might have a noticeable effect on the Io torus, a torus of high-energy particles connecting Jupiter with the highly volcanic moon Io. High-resolution spectroscopic studies found that variations in the ion density, rotational velocity, and temperatures at the time of impact and afterwards were within the normal limits. Section 6. Post-impact analysis. One of the surprises of the impacts was the small amount of water revealed compared to prior predictions. Before the impact, models of Jupiter's atmosphere had indicated that the breakup of the largest fragments would occur at atmospheric pressures of anywhere from 300 kilopascals to a few megapascals, or from 3 to a few hundred bar, and most astronomers expected that the impacts would penetrate a hypothesized water-rich layer underneath the clouds. Astronomers did not observe large amounts of water following the collisions, and later impact studies found that fragmentation and destruction of the cometary fragments in an airburst probably occurred at much higher altitudes than previously expected, with even the largest fragments being destroyed when the pressure reached 250 kilopascals, or 2.5 bar, well above the expected depth of the water layer. The smaller fragments were probably destroyed before they even reached the cloud layer. Section 7. Longer-term effects. The visible scars from the impacts could be seen on Jupiter for many months after the impact. They were extremely prominent, and observers described them as more easily visible even than the Great Red Spot. A search of historical observations revealed that the spots were probably the most prominent transient features ever seen on the planet, and that while the Great Red Spot is notable for its striking colour, no spots of the size and darkness of those caused by the SL9 impacts have ever been recorded before. Spectroscopic observers found that ammonia and carbon sulfide persisted in the atmosphere for at least 14 months after the collisions, with a considerable amount of ammonia being present in the stratosphere as opposed to its normal location in the troposphere. Counterintuitively, the atmospheric temperature dropped to normal levels much more quickly at the larger impact sites than at the smaller sites. At the larger impact sites, temperatures were elevated over a region 15 to 20,000 kilometres wide, but dropped back to normal levels within a week of the impact. At smaller sites, temperatures 10 kelvins higher than the surroundings persisted for almost 2 weeks. Global stratospheric temperatures rose immediately after the impacts, then fell to below pre-impact temperatures 2 to 3 weeks afterwards, before rising slowly to normal temperatures. Section 8. Frequency of impacts. Since the impact of SL9, 2 further very small comets have been found to be orbiting Jupiter. Studies have shown that the planet, by far the most massive in the solar system, can capture comets from solar orbit into Jovian orbit rather frequently. Cometary orbits around Jupiter are generally unstable, as they will be highly elliptical and likely to be strongly perturbed by the Sun's gravity at apogee, the furthest point on the orbit from the planet. Studies have estimated that comets probably crash into Jupiter once or twice per century, but the impact of comets the size of SL9 is much less common, probably no more often than once per millennium. There is very strong evidence that comets have previously been fragmented and collided with Jupiter and its satellites. During the Voyager missions to the planet, planetary scientists identified 13 crater chains on Callisto and 3 on Ganymede, the origin of which was initially a mystery. Crater chains seen on the Moon often radiate from large craters and are thought to be caused by secondary impacts of the original ejecta, but the chains on the Jovian moons did not lead back to a larger crater. The impact of SL9 strongly implied that the chains were due to trains of disrupted cometary fragments crashing into the satellites. Section 9. Jupiter as a cosmic vacuum cleaner. The impact of SL9 highlighted Jupiter's role as a kind of cosmic vacuum cleaner for the inner solar system. Studies have shown that the planet's strong gravitational influence leads to many small comets and asteroids colliding with the planet, and the rate of cometary impacts on Jupiter is thought to be between 2 and 10 times higher than the rate on Earth. If Jupiter were not present, these small bodies could collide with the inner planets instead. The extinction of the dinosaurs at the end of the Cretaceous period is generally believed to have been caused by the impact event which created the Chicxulub crater, demonstrating that impacts are a serious threat to life on Earth. Astronomers have speculated that without Jupiter to mop up potential impactors, extinction events might have been much more frequent on Earth, and complex life may not have been able to develop. This is part of the argument used in the rare Earth hypothesis. External links. Comet Shoemaker-Levy 9 frequently asked questions. http://www.physics.sfasu.edu/astro/sl9.html. Comet Shoemaker-Levy 9 photo gallery. http://www.seds.org/sl9/sl9.html. Jupiter swallows Comet Shoemaker-Levy 9. http://apod.gsfc.nasa.gov/apod/ap001105.html. Comet Shoemaker-Levy collision with Jupiter. http://www.jpl.nasa.gov/sl9/sl9.html. National Space Science Data Centre information. http://nssdc.gsfc.nasa.gov/planetary/comet.html. This sound file and all text in the article are licensed under the GNU Free Documentation License, available at www.gnu.org/copyleft/fdl.html.